Weight shift control for powerplants. Let's discuss here the fuel quantity gauge in weight shift control aircraft indicates the amount of fuel measured by a sensing unit in each fuel tank, displayed in gallons. While the gauge provides valuable information, it's crucial not to rely solely on its accuracy. Pilots should visually inspect the fuel level during the pre-flight inspection and compare it with the corresponding fuel quantity indication. Additionally, tracking in-flight fuel consumption is important, and pilots should be aware of the approximate consumption rate by consulting the pilot's operating handbook, PO, to ensure sufficient fuel for the flight. If an auxiliary electric fuel pump is installed, a fuel pressure gauge might be included, indicating the pressure in the fuel lines. The normal operating pressure can be found in the PO. After leaving the fuel tank, the fuel passes through a filter before entering the fuel pump or carburetor. This filter removes sediments that may be present in the fuel. Aviation gasoline, AVGAS, is identified by an octane or performance number, designating the anti-knock value or knock resistance of the fuel mixture in the engine cylinder. Higher grade gasoline can withstand more pressure without detonating. Lower grade fuels are used in lower compression engines, while higher grades are used in higher compression engines. If the proper grade of fuel is unavailable, the next higher grade can be used as a substitute. It is important never to use a lower grade, as this can lead to cylinder head temperature exceeding the normal operating range and result in detonation. AVGAS 100 low lead, LL, despite its name, contains more lead than the old leaded gas from automotive filling stations. While it degrades slower than auto gas and has a standardized composition worldwide, it may not be recommended for certain two-stroke engines due to lead-related issues. Now, for two-stroke engines, manufacturers generally recommend the use of 89 octane minimum auto fuel. Mixing 100LL and auto gasoline in a 50-50 ratio can be a reasonable compromise when the proper auto gas octane is unavailable. Methanol alcohol, with corrosive properties, should not exceed 5% in fuel, while ethanol, which attracts water, should not exceed 10%. Manufacturers provide specific recommendations, and pilots can conduct a simple test to measure alcohol content using a sump collector. When methyl tertiary butyl ether, MTBE, added to fuel to improve air quality, lacks corrosive or water-attracting properties but has been banned in some states due to carcinogenicity. It is found only in some higher-grade fuels. So, when it comes to flying weight shift control aircraft, having clean fuel is absolutely crucial for a safe ride. You wouldn't believe how many powerplant hiccups are linked to fuel contamination issues. One big culprit is rust, especially in metal fuel containers. To tackle that, it's a good idea to fill up those metal tanks after each flight or, at the very least, after the last flight of the day. Moisture can really mess things up. Now, refueling can be a bit of a procedure. Refueling from cans or drums? Watch out for contamination. Using a water filtering funnel or one with a chamois skin can help, but here's the catch. A worn-out chamois won't filter water, and a brand new one that's already damp won't either. Oh, and letting fuel sit around for too long. Not a great idea. It can go bad or lose its octane over time. And if you're dealing with pre-mixed gasoline and two-stroke oil, well, that adds another layer of complexity. The gas might evaporate in a plastic container, leaving you with a richer oil mixture. Now, refueling procedures need some attention too. Never mix oil and fuel in an enclosed space. Those fumes can be irritating and, with the right mix, even cause an explosion. When you're dealing with metal and plastic containers, they both have their pros and cons. Metal cans protect fuel from UV rays but might sweat in humid weather. Plastic ones are easier to handle and won't scratch your aircraft's finish, but they can accumulate static electricity, especially sliding around in the back of a pickup truck. And speaking of static electricity, that's a real concern during refueling. Grounding the aircraft and bonding the nozzle, chamois filter, and funnel is key to preventing sparks. Moreover, for those two-stroke engines, you've got to mix in the right two-stroke oil with the fuel. Some engines have nifty oil injection systems that do this for you, but if not, grab an approved container, mix that oil and fuel together, and shake it up well before adding it to the tank. Let's dive into the heart of an aircraft, its starting system. Picture this. Most small aircraft are like modern virtuosos, equipped with a direct cranking electric starter system. Now, this system is akin to a finely tuned orchestra with components like a source of electricity, wiring, switches, and solenoids orchestrating a symphony with the starter and its motor. The starter, our leading performer, gracefully engages with the aircraft's flywheel or gearbox, setting the engine in motion at a pace that ensures a smooth takeoff. Now come to the electrical power, as usually supplied by an onboard battery. When you flip that battery switch to on, electricity takes center stage, flowing into the main power bus through the battery solenoid. Both the starter and the starter switch draw their energy from the main bus, but here's where it gets interesting. The starter won't take its cue until the starting solenoid feels the energy, activated by turning the starter switch to the start position. And as you release the starter switch from this position, the solenoid gracefully removes power from the starter motor. But we've got a clever trick up our sleeves. A clutch in the starter drive prevents the starter motor from being driven by the engine, allowing the engine to rev faster than its starter companion. Now, let's shift gears to the lifeblood of our four-stroke engines, the oil system. Imagine it as the engine's guardian angel, handling multiple responsibilities with grace. Its duties include providing a lubricating touch to the engine's moving parts, orchestrating a cool down by reducing friction, extracting heat from the cylinders, ensuring a snug seal between the cylinder walls and pistons, and performing a cleanup job by escorting away contaminants. Our four-stroke engines sport either a wet sump or dry sump oil system. Now, isn't it fascinating how these intricate systems come together, each playing a vital role in the grand performance of our aircraft? Let's dive into the intricacies of engine cooling, a vital act in our aircraft's performance saga. Imagine this. Within the cylinders, the burning fuel orchestrates an intense heat, and while most of it gracefully exits through the exhaust system, there's a lingering warmth that needs a different stage to perform on, or rather, be dissipated. Now, in the realm of our weight shift control engines, there's a choice to make. Will it be air-cooled or liquid-cooled? A bit like choosing between a breezy concert and a liquid-cooled symphony. Many of our weight shift control aircraft flaunt a cylinder head temperature gauge, a maestro of sorts, signaling an immediate temperature change in degrees Celsius or Fahrenheit. The recommended temperature ranges? Find those golden numbers in the aircraft's PO, AFM, AOI, our trusty guides in this musical journey. Air cooling, a performance art in itself, unfolds with a cooling fan pulling air into the engine shroud. Ingenious baffles guide this air ballet over fins attached to the engine cylinders, where it gracefully absorbs the engine's heat. The grand finale? The expulsion of hot air through openings in the shroud. But, beware. If the cylinder head temperatures in an air-cooled engine take an unexpected rise, it could be due to lubrication glitches, cooling fan drive belt mishaps, or even a blockade in the cooling fins, perhaps by a bird's nest or a whimsical insect. In another corner of the orchestra, we have liquid cooling systems, a sophisticated ballet of coolant pumping through jackets in the cylinders and head. This heated liquid then waltzes to a radiator, where the heat is sent off into the atmosphere, ensuring a cooled-down encore as it returns to the engine. Place the radiator close to the propeller, and you've got a perpetual breeze, keeping the engine chill even when the weight shift control is resting. Now, about that engine warm-up, a crucial prelude to our symphony. Consider it a gentle wake-up call to avoid engine damage and seizures. Gearboxes take the stage, reducing the engine RPM to a propeller-friendly beat, while induction systems concoct the perfect gas and air mix, adjusting gracefully to different altitudes. Now we delve into the engine's heartbeat, the ignition systems. These systems, a bit like a well-orchestrated band, include a magneto or generator, control box, high-voltage wires, spark plugs, and ignition switches. Oh, and let's not forget, unlike automotive engines that run their ignition system off the battery, our aircraft have a separate realm for ignition, adding an extra layer to this musical composition. As our engines balance between proper combustion, fuel management, and cooling considerations, we conclude here a rich symphony of engineering, where every component plays a vital role in ensuring a reliable and harmonious flight.